All right, let's go ahead and get started. As you can see, we're on the last leg of our semester. We're going to do at least 3 sections today, and probably if not finish up Wednesday, we'll finish up next Monday. And then that'll give you the rest of the time for you guys to catch up and do your work. So let's begin. Inverse functions. If you remember, last class, we looked at something called the composite functions. Where each of these have their particular meaning, where f of x and g of x are functions. What does this mean? What does that mean? What's another way of writing it? Okay, then give you another one. If I give you this, how would you write that? Yes. I can see you guys are on top of it. Composite function is read f of g. That's the way it's read. So it's this says is the f function of the g function. The g function is of x. It's the variable that's inside it. So what this is read is this function goes in place the x values in the outer function. What this one says is f of x. Now, I'm not going to review all that because that's what you guys should have done over the weekend. But the reason we need this is because now we're going to look at what are called inverse functions. This little -1 exponent tells us that it's an inverse function. It does not mean 1 over f of x. It simply means the inverse. What's the inverse of 3? Why -3? What is the definition of inverse? You've heard it before, you've seen it before. This means opposite, not inverse. The way we know something's an inverse, I'll show you that in a second, is the only way we can prove if it's an inverse is by using composite functions. But it's a safe, everybody always says that. So you're in good company. Every class I've ever taught, I even said that when I was in your seat. So you're in good company. How to find an inverse. So first, let's begin by looking at these numbers as a set notation. This is set A, and these are the 4 points that make up set A. The inverse of set A looks like this. You have to have the same number of elements, but what do we notice about it? The X and Y coordinate are switched. Which is how we find the inverse. Which is how we find the inverse. We switch X and Y. So let's look at example 1. If G is equal to 2, 4, -1, 3, -2, 0, find the inverse of G. This is the inverse. Let's see. So what's the inverse going to be? It's going to be what? You asking or telling? Yes, so switch X and Y. And the next one's going to be 3, -1, 0, -2. Let's look at them, graph them. So the first one is 2, 4. I'll make those zeros. -1, 3. And -2, 0. Let's look at the inverse graphs. 4, 2, make those x's. 3, -1, and 0, -2. So if we plotted these points and graphed them, what do you notice about the two graphs? Over what? The x-axis here. So is it going up and down? No. Y-axis here. That means this one would be down here. No, you're getting close there. You're given 2 million more tries, you'd get it. No, it's across the line y = x. If you think about it, what did we do? We switched x for y. So that's why it's symmetric about the diagonal line y = x. Because we switched x for y. So whenever you graph something, if I give you a graph, then just draw the y = x line and mirror image of it. Just take it and fold it and just poke dots. It makes it much easier that way. So let's look at finding the equation of inverse functions. Let's look at this one. Find the inverse of y. To be honest with you, everything you need to know, we've talked about already. How do we find the inverse if I give you a set of numbers? Not signs. What are we flipping? Yes, what do the numbers represent? You're getting close. You're getting close. What do we do for our graph? How do we get the inverse of it? Switched what? Switch x and y. Yes. So the first thing we do is switch x and y. Here are the steps. The steps to find the inverse. First off, switch x and y. Then solve for y. That y will be your inverse. So our first step, we switched x and y. Now we're going to solve for y. So what do we do first? Subtract 2. X minus 2 equals 3y. Then divide by 3. So my inverse is x minus 2 over 3. How do we check it right now? Well, to check, we can find points. The points on y. So for example, let's create a chart. Let's try -1, 0, and 1. So if I put -1 inside my original function, what do I get? No. Yeah, -1 times 3 is -3, plus 2 is -1. If I put 0 in there, what do I get? 2. And if I put 1, so these are the points of my original graph. How do I check this one? Put in the y's. Now I put in the y values and see if I get the x values. So if I put -1 in there, or 2, or 5, what do I get? So -1 minus 2 is -3. -3 over 3 is -1. Check, that works. 2 minus 2 is 0, over 3 is 0. Check, that works. 5 minus 2 is 3, 3 over 3 is 1. Check, that works. So that's one way I can check it. There's another way I'm gonna show you in a second. But this is what we talked about so far. We looked at our graphs, we looked at switching X and Y's. That's exactly what it's talking about. Let's look at example 2. You want to take a picture of this side? You want to take a picture? Example 2 says, find the equation of the inverse of this equation. So what's my first step? Since I'm looking for the inverse, I got to switch X and Y. Now I got to solve for Y. Is it possible? Not possible. Y does not have an inverse. Because it is not 1, 2, 1, or 1. Right. For 1 to 1 is for every one X, there's one and only one Y. 1 to 1 functions for each X, there is one and only one Y value. So basically it says this. For every X value, there can only be one y value associated to it. Is this set 1-to-1? Is that set 1-to-1? Is it one? What's that? So is it yes or no? It's a yes or no question. You say no. What do you say? No? Everybody says no? Everybody's wrong. Remember, for every X value, are all the X values different? No, these are the same. Are the Y values different? So this point and this point is the same. And since all the other X values are different, that's all that matters. So yes, it is 1-to-1. So if all X values are different, then it is 1-to-1. If any X values are the same, they better have the same Y values. The same. So that's if I give you a bunch of points, a set of points, I should say, not a bunch of points. How can we tell graphically? How can we tell graphically if a function is 1-to-1? Yes. Back graphically, if it passes the vertical line test, then it is 1-to-1. So what does this mean? If a function is 1-to-1, what does that mean? If a function is 1-to-1, the first thing it tells us, it has an inverse. So if a function, then it has an inverse. What else does that mean? Remember, we switch X and Y. So what it tells us here is here's our function, here's our inverse. The domain here is the range there. The range here is the domain here. Because you switch X and Y. So that's what it's telling us. So if you look at a graph and it said that's why it's diagonals at 45 degrees, the Y equals X. The X of one equals the Y of the other. That's what that says. Example 3. Given the function f described by f of x equals 2x minus 3, prove that it's 1-to-1. If it's 1-to-1, then what do we know has to exist? The inverse. So if we can find the inverse, then it's 1-to-1. Well, if we can find the inverse and the inverse is 1-to-1, then it's a true inverse. The first step is what? Switch X and Y. Second step, solve for Y. So add 3 to both sides. X plus 3 equals 2y. And divide by 2. And there we go. A inverse exists. So therefore, this function is 1-to-1. Example 4. Prove that this function is not 1-to-1. First off, we got to find the inverse, see if it exists. So we switch X and Y. How do you get Y by itself? Whenever you square root a squared term, what happens? It becomes plus or minus. Is it 1-to-1? No, because for any one value of X, there's a plus or minus Y that goes around with it. In other words, that's the original function. That's the inverse. It fails the vertical line test. We notice something here. The original function, okay, the inverse fails the vertical line test, but the original function fails what's called the horizontal line test. If the original function has two y values, or the same y values for two x equations, then it fails the horizontal line test. That means it's not going to have a inverse. The horizontal line test on your sheet says, if the horizontal line test is if your original function, if a horizontal line crosses at 2 points, 2 or more points, then it's not to 1, and the inverse is not a function. That means it won't exist. So if the original function If you draw a horizontal line with the original function and only crosses it once, then the inverse is going to exist, and it's going to be 1-to-1. It's going to be a function. Example 5. From the graph shown, determine whether the function is 1-to-1 and thus have an inverse. Does the first one have an inverse? Yeah, because it passes the horizontal line test. How about the second one? No, it fails the horizontal because it crosses at 2 points. The third one, C, does that one pass the horizontal line test? Yeah, because I could draw any horizontal line, it's only going to cross it once, therefore it's going to have an inverse. How about the last one? No, it fails on many counts. So it's not going to be an inverse. All right, example 6. Determine whether the function is 1-to-1. And if it is, find the inverse. So is it 1-to-1? How do we know it's 1-to-1? What kind of equation is it? It's linear. All linear equations are 1-to-1. So it is 1-to-1. So we got to find the inverse. First step, switch X and Y and solve for Y. Now I'm going to show you another way of finding if the inverse is a true 1-to-1 function using composite functions. If f of x and f of x are inverse functions of each other, there. If it's an inverse function, then the composite of both ways has to give you a value of x. So let's try it with our just the one we just did. If f of x was 2x minus 3, and the inverse, which we calculated, was x plus 3 over 2, are they true inverses of each other? You have to try both of them, and they both have to equal x. Remember what this one says. So what this one says, I take my inverse function, I take this equation, anywhere I see an x in the original, I put it in place of x. So it's 2 times x plus 3 over 2 minus 3. That's what this one says. So the 2's cancel, so we have an x plus 3 minus 3. The 3's cancel, it equals x. That's the first one. Now I gotta do it the other way. This one says I take the original function. Anywhere I see an x in the second one, in the inverse, I put it in there. So I have 2x minus 3 plus 3 over 2. 3's cancel. 2x over 2, the 2's cancel. So they're inverses. So that's another way you can check to see if it's true inverses. And example 7 we did already. It's just graphing those points. They're both linear, so we plot a couple of points, and you'll see that they're reflective across the y equals x-axis. Let's look at example 8. Consider this function. A. Is it 1-to-1? B. Find the inverse. Graph G and G inverse. So is it 1-to-1? Well, is there a horizontal shift? No, there's nothing inside there. Is there a vertical shift? 2 spaces. Oh, it just goes up 2. So it is 1-to-1 because it passes the horizontal line test. Remember, the cubic function is always an increasing function. So we have to find the inverse. So here's another rule of thumb. If the degree is even, it's not 1-to-1 because it fails the horizontal line test. If it's odd, then it may or may not pass the horizontal test. Because remember, a cubic function can also look like this, which it'll fail the horizontal line test there. But that all depends on what the function looks like. So the first thing we gotta do is switch x and y and solve for y. Then I cube root both sides. So the inverse equals the cube root of x minus 2. So how do you graph this one? What does the cube root function look like? It's like that. But it shifts to the which direction? If you don't remember, set it equal to 0. positive, so it shifts to the right. It's always the opposite of what's happening inside there. So if we look at our original graph up here, it's diagonal. It's a mirror image of it. This is G, this is G inverse. So far, so good. And example 9. It says, prove that f of x and g of x are inverses by using composite functions. So we got to do the composite function thingy. All right. Don't bobblehead. Work it out yourself first. Because you're always waiting until I write down before you do anything else. Do it yourself first. Good. N equals X. And you can see, yes, they both equal X. For the first one, take the inverse, plug it in place of X of the first. The 5s cancel, then the 8s cancel. And then take the function, put it inside the X inside the inverse, and everything cancels. So it's a true inverse. Any questions about that?